This is session number 13, identifying peaks manually. This is mainly used for survey spectra. We are once again going to use the native oxide of silicon. It's a convenient spectrum because it has not so high counts and little noise and small contaminant peaks. So how do we do this manually? Well, as we have shown you before, the first thing to do is to select find peaks, find integrate peaks, and then to select the background, put the mouse anywhere and press the left mouse button. Now the black lines become permanent. They replace the red dotted lines. Now we can go in individually if we want to and just label each of these peaks. For example, this peak, because I'm doing this for a long time, I know it's oxygen. We got to put a space in, 1S. Then you should see the RSF number, the sensitivity factor number, appear. You press calculate because you want it to be part of the display. You can see here now the oxygen is ready. We know this is carbon. Carbon's on everything, so we manually go in, choose again, peak with a question mark on it. We want to calculate that. You can see the binding energy of that peak, and we type carbon space 1S. Okay, 1 is the sensitivity factor. We know nitrogen appears on many things, so we know this is nitrogen, or we think it is nitrogen. We can always change it. So we calculate the atom percents. It's a 403 number. That's more likely a nitrogen with an oxygen. It could be an ammonium. So nitrogen space 1S. And then we know we got silicon here, so these two peaks down here at 100 and 150 are the major silicon peaks. So we'll label this manually. And we want to calculate it. So we want Si2P. All right. And this one right here, this is the silicon 2S. So we don't calculate that one because we can only use one of the peaks for calculating atom percents. You might have 10 peaks for an element, but you can only use one of the peaks if you want to calculate the correct atom percents. So this is Si space 2S to get the label. And if you're happy with that, you're done. You could delete these other points. This is oxygen OJ. Let's go back to the arrow. I'm sorry, the spectrum with a question mark. I want to call that oxygen OJ. I could give it a different name. I could add KLL to it. Okay, once I accept it, it's displayed over here. There are always loss peaks. Okay, silicon has loss peaks. That's what you see here. You might also think of them as satellite peaks. Okay, it depends on the chemical state. Oxygen has an energy loss peak. They're typically about 15 to 20 volts higher in binding energy than the main peak. So this should be oxygen loss. So we're going to identify that manually. Okay. Now this is a weak little signal. It's a doublet. Okay, what kind of doublet typically appears around 488? I forget. So I go to the spectral lookup lines table. I go down here to about 485, and that's in this region. Now, what is likely? What has a peak there, which should have been a very big peak if it was pure, but in this case, we just have a tiny amount, so it's going to be, has to be a major signal. Gallium, tin's a real possibility. Holmium, no. Here's the other tin. All right, we got a doublet there. All right, so let's choose tin. And it lines up in multiple places, so good, we'll add that. And actually, up here is another little peak, if you can see it. That would have been another tin peak. This is a peak, 688. That's fluorine. Fluorine is almost on every silicon wafer you analyze, unless they've done some special work to get rid of it. So we want to calculate that. Fluorine 1s, accept. All right, so it looks like we're all done. We haven't labeled these guys. These are loss peaks, silicon loss peaks. So we'll go back to our, and we'll call it silicon loss. And I'm going to be lazy. I'm going to copy that and hit accept. Now this next one is another silicon loss. It overlaps a little with tin 4s, but there's so little tin, ignore that tin presence. Okay, paste, accept, do the next one, paste, accept, do the next one, paste, accept, and the final one. Paste, accept. All right, we got everything labeled. Now, I want to show you one last thing. It's going to make this a little longer, but it's a useful thing. We'll bring up the pop-up screen again. Let's say we got some peak, we don't know what it is. And so what we do, we go over here and select a very low atomic number. And then we keep hitting the down arrow key. Okay, and you can see the potential peaks come in. All right, when you get a set of peaks that match what you have there, that's a very probable assignment. Here we can tell this is where aluminum should appear, but you got no aluminum. Okay, otherwise you would see a peak there. Okay, magnesium, you don't have magnesium. Sodium, you should have a peak there. Neon, no neon. So that's another way to use the XPS spectral lines table. That's it for this lesson. Thank you.